Previously, we had looked at the arc length integral, and that was an integral from a to b that would give us the length of a curve from a to b. Now we want to look at something called the arc length function. If you look at that, it looks very similar to what we had for arc length. Notice what it's doing, though. It's starting, x naught is some actual value. We'll start there, but we're not specifying the ending value. We're leaving that as a variable. And because we're leaving that as a variable x, just to distinguish it from the integration variable, we've used a dummy variable t. So we've replaced that x in our formula with a t. These will become x's in the integration. The idea is if you needed to calculate various lengths on the same curve with the same starting point, you would only do the integration one time. That would create a function of x. And then by plugging in different x's into that function, you could find different lengths from different locations along the curve. So the idea is you do the integration once, and now you have a general purpose for that particular curve, a general purpose length function, hence the name arc length function. So let's do an example of creating an arc length function for a given curve. And for our example, let's just use the same function we used previously. So for example, let's use our y equal x to the 3/2. And let's start out at x equals 0. So this x naught, or x sub 0, is just your starting point. You have to have some fixed starting point. But notice, unlike our example of arc length, we're not specifying an ending point. All right, so we've done some of this work already. We know what this integral looks like. We've taken the derivative. So first of all, just to clarify, this is just a dummy variable that we switched to, so there's no confusion between variables there. So you can rewrite this as f of t is t to the 3/2. OK. So starting from our given starting point here of 0, and then not specifying an endpoint, and then the integral 1 plus, we did this already. We know that the derivative of that squared ends up being 9/4 t. And we'll do our integral. And we've already done this. We saw that we had to divide by 9/4 or multiply by 4/9. And then that was 1 plus 9/4 t to the 3/2. And when you divide by 3/2, that's multiplying by 2/3. But now we're going from 0 up to x. So far this looks just like our example, except for we're using a t here instead of an x. And we're no longer saying end at 4. We're just saying end at some unknown value. So we saw that those constants just make 8/27. And then 1 plus 9/4. When you plug in x for t, you just get 1 plus 9/4 x to the 3/2. And when you plug in 0 for t, you just get 1 to the 3/2. And that's our arc length function. So what have we done? We've created this function s of x. Now, for example, our previous calculation, we wanted to go from 0 to 4. You would plug 4 into here, and it would tell you the length of the curve. If you want to go from 0 to 100, plug in 100 here, and you get the length of that curve. Go from 0 to 16, whatever you pick. You've done the integration once generically, and now this is a reusable function that'll tell you how long the curve is from that same starting point. And in applications, often there's a starting point that makes sense. Maybe this is at the beginning of the trajectory of an object moving along a path, but there might be some natural starting point, and this function gives you all the arc lengths from that starting point.